Hello everyone. In this video, we're going to be looking at limits at infinity. So what I mean by that is we want to take a look at the limit of a function as x approaches infinity. And another way that I can explain that is that what happens to our function values as our values of x get very, very large in the positive direction, or they get very, very small in the negative direction. Let's start off with a simple example to try and make sense of this a little bit more. Let's look at the function f of x is equal to 1 over x. And what we want to investigate, let's do the limit as x approaches infinity of this function. Okay, again, just as a reminder, infinity here is not a number, but what that represents is x is becoming unbounded, right? It's increasing without bound. So to start off, why don't we make a table of values? So we're going to pick out some x values, and we want these x values to get increasingly larger. Okay, so let's pick out some values. Maybe we'll start with an x value of 1, and then maybe we'll do powers of 10. So we'll jump up to 10, we'll do 100, we'll go up to 1,000. Maybe we'll jump up here to 100,000. We just want these x values to keep getting larger and larger. So now if we plug these in, let's see what we get. So 1 over 1, we get 1. So it's just the reciprocal function. So 1 over 10, 1 over 100, 1 over 1,000, and 1 over 100,000. So if I take a look at these function values, as my x values keep getting larger, the function values keep getting smaller. So what's going to happen here is as I keep going towards positive infinity, these values are going to be approaching 0. So another way I can say this is I can get as close to 0 as I want as long as I can pick out an x value big enough. So you can give me something that's very, very close to 0, and I can find an x value that's big enough that will get me that close. We're never actually going to get to 0, but I can get sufficiently close enough to say that the limit is 0. So our limit as x approaches infinity of 1 over x, this is equal to 0. If we take a look at a graph of this, we can see that as these x values are getting larger and larger, my function values are getting closer and closer to 0. Another way I could describe this is the end behavior of this function. So I have a horizontal asymptote at 0, and that's what these function values are approaching. We have a similar case if I look at the limit as x approaches negative infinity. So as I approach negative infinity of 1 over x, as I become unbounded in the negative direction, it's also approaching 0. And these two facts, these are really important, and they're going to help us find the limits as we approach infinity or negative infinity of some other functions as well. So keeping these in mind, let's do a couple examples. So here I have the limit as x approaches infinity of 2 plus 3 over x. Now, as we approach infinity, these limits, all of the limit properties do apply. So the property, the sum of a limit, the difference of limits, product, quotient, we can use all of those as we work with these. So for example, in this first one, I have a sum. So we can actually separate this and write this as the sum of two limits. So we end up with the limit as x approaches infinity of 2 plus a second limit, the limit as x approaches infinity of 3 over x. All right, here I have 3 times 1 over x, if I want to think about it that way. So I can use the property for a constant, and I can bring that out front. So I'm going to go step by step here. I have the limit as x approaches infinity of 2. And then instead of writing this as 3 times 1 over x, let's write this as 3 times the limit as x approaches infinity of 1 over x. Okay, so we broke it down using our properties, and now we can actually evaluate this. So the first limit, the limit as x approaches infinity of 2, that's just the limit of a constant. So that is always just going to be whatever the constant is. So this is just 2. Then we have plus, and we have our 3. And now this this is what we just talked about. We just established this fact. So the limit as x approaches infinity of 1 over x, again, if you imagine plugging in bigger and bigger and bigger numbers into x, that's going to get closer and closer to 0. So that we end up with 3 times 0. So then we have 2 plus 0, so our final answer, our limit, is equal to 2. So using some limit properties, we were able to expand this out and then evaluate it. Now, sometimes it's not given to us in a way that we can do that right away, and that's what these next two examples are going to look at. So in this case, I have the limit as x approaches infinity, and then I have this rational function, 3x squared minus 2x plus 8 divided by x squared plus 1. So again, if I think about just substituting in infinity, it's not going to work out for me. If I just plug in numbers of x that are getting bigger and bigger and bigger, I'm not going to be able to come up with a limit, right? So instead, we want to try and revert this back to those two facts we established earlier. So the limit as x approaches infinity of 1 over x, we know what that's going to be. So the first thing I'm going to do is I'm going to divide the numerator and the denominator of this function by the power of x, the largest one that I have in my denominator. In this case, that's going to be dividing by x squared. So let me write all that out. The limit as x approaches infinity, and then we're going to divide the numerator and the denominator by x squared. Okay, it's important to note that I'm not changing the value of my function at all. Essentially, I'm dividing by 1, okay? Since we're doing the same thing to the numerator and the denominator. But now we can split this up and we can do a little bit of simplifying. So the limit again, as x approaches infinity, and then I'm going to separate all of these out. So we have 3x squared over x squared minus 2x over x squared plus 8 over x squared. And then the same thing in the denominator. Okay, so now, written like this, we can do some simplifying. So I'll bring it up here. So we have our limit as x approaches infinity. And now we can simplify. So we have just 3, because the x squared cancel out. Our middle term, one of those x's will simplify. So we end up with 2 over x. And then we'll have plus 8 over x squared. In the denominator, we have 1 plus 1 over x squared. So from here, I can use more of my properties to separate this if I would like. We have the limit of a quotient. So I could rewrite this as the quotient of two limits like this. Okay, and I could keep going. I could separate this. So we have some differences, we have some sums, so we could separate everything. And then we could go even further, and we have some constants we could take out. But what I want you to notice here is if we look at what we end up with, remember the big idea is as I plug in numbers of x that are getting bigger and bigger, the denominators are getting bigger and bigger, which makes these fractions approach 0. So if I look at each of these, and this is why we divided by x squared, so here we have a constant, but my second term I have 2 over x. So if this x value keeps getting bigger and bigger and bigger, this fraction is going to get closer and closer to 0. The same thing with the second one. 8 over x squared, as I plug in bigger and bigger x values, this one's actually going to get closer to 0 faster, right? Because we're squaring them. In the denominator, we have another constant, but then we have 1 over x squared. So as I plug in numbers that are getting bigger and bigger, this fraction will also get closer and closer to 0. So what that means is for my limit, I have 3. That second fraction is getting closer to 0. The 8 over x squared is also getting closer to 0. In the denominator, we have 1, the limit of a constant. And then the 1 over x squared is also getting closer to 0. So simplifying that whole thing, our limit is equal to 3. Let's try that process one more time with a similar example. So the limit as x approaches infinity of, again, another rational function, 2x cubed minus x plus 10 divided by 5 minus x to the 4th. Again, the process here is I'm going to start by dividing everything by the power of x, the biggest one in the denominator. And in this case, that means everything, every term is going to get divided by x to the 4th. So let's write that all out. The limit as x approaches infinity, 2x cubed, and now every term we divide by x to the 4th. All right, now let's do some simplifying. Let's see what we end up with for these fractions. So that first one in the numerator, the x cubed divided by x to the 4th, we're going to end up with 2 over x. In the middle, we have one of the x's will simplify, so we get 1 over x cubed. And then we have 10 over x to the 4th. In the denominator, we're going to end up with 5 over x to the 4th minus 1. So again, we do have a limit of a quotient. We could turn this into the quotient of some limits. We could use our other properties to keep separating this further if we wanted to. But again, what I'm hoping you notice here is because of these fractions and because we have x's in the denominator now, we can think about what happens as x becomes unbounded. So in this first fraction, we have 2 over x. Okay, so the limit as x approaches infinity for this is going to get closer and closer to 0. So we'll write that over here. So that first one, we end up with 0. The middle one, 1 over x cubed, as those x values get bigger and bigger, that also approaches 0. So minus 0. And then the same thing for the last one. So 10 over x to the 4th. So as those x values get bigger and bigger, that will also approach 0. In the denominator, 5 over x to the 4th, that limit is 0. And then we have the limit of a constant, which is just 1. Simplifying this, we end up with 0 over negative 1. So we just end up with 0. So our limits of this entire function, the limit as we approach infinity, as our x values become unbounded, this is equal to 0. And again, relating this back to what we started with, this is the same as the end behavior of this function. So if I were to graph this, I should be able to see that as my x values get bigger, as I approach positive infinity, I should have a horizontal asymptote at 0.